All right. Hello, everyone. Thank you all for joining us today for what promises to be an insightful webinar. I am Safa, and I'm very happy to be welcoming you today. Before we dive into today's exciting topic, let me take a moment to introduce you to Morocco HPC. So, our initiative actually started not so long ago, and it was launched with a mission to bring HPC closer to professionals, researchers, and enthusiasts in Morocco. We actually want to create a vibrant HPC community in Morocco. And we want to do that. We want to get there by hosting webinars, organizing workshops, training sessions, all for the sake of sharing knowledge and collaboration, not only with local experts, but also with global experts. Today's webinar is actually part of our ongoing effort to explore how HPC is enabling cutting-edge technologies across various fields. Now, on to the reason why we're all here, large vision models. So these models, integral to artificial intelligence, are actually being used to solve a lot of complex problems, for example, in healthcare, autonomous systems, and other fields. But training these models, especially when it's done at scale, requires immense computational power. So this is where parallelization on HPC systems plays a very, very important role. So in today's webinar, we will explore how HPC infrastructures make it possible for efficient training and also to optimize these large models. I am very honored to introduce our speaker, Dr. Sharma. Dr. Sharma is a leading expert in AI and HPC with over 15 years of experience in the field. She has a PhD in artificial intelligence, and her work spans research, global speaking engagements, and AI innovation. Today, she will share with us her invaluable insights on parallelizing large visual models using HPC systems. Dr. Sharma was actually one of the very first people I talked to about Morocco HPC, and she was very nice to give me a lot of advice and to share with me a lot of tips. So I'm very happy on a personal level to have her with me here. Now, thank you very much for accepting my invitation. And without further ado, I'll hand it over to you. Welcome again, and we're looking forward to your presentation.
Thank you, Safa, for the kind introduction. I am really honored to be here and excited to share my views on one of my favorite research topic, which is the convergence of high-performance computing and artificial intelligence. Today, I'll definitely talk about the large vision models which are shaping the future of AI and driving new innovations in the convergence of HPC and AI through the various parallel approaches on the advanced accelerators. I'll start with the contents here. I'll start talking about the why does AI need HPC. This is the very from the question to all the researchers of HPC and AI. Why computer vision models are heavily depends upon the HPC systems, and what is large vision models, current state of the art large vision models, and different ways, different approach to train those large vision model in the parallel manner on different HPC systems, along with the advanced accelerators, which are specialized for the large vision models, and the takeaways which we learned from this session. So AI research especially know about why deep learnings are heavily depend on the HPC systems. Here I will give a brief about the deep learning models. They are highly complex, and if we go deeper into the layer-wise architectures, they became more computationally intensive and require significant resource to process large data sets. These models are enabled with the multimodal capabilities, integrating different data types, for example, text and images, videos as well. The high performance infrastructure is essential for efficiently accelerating training in less time. The modern computer vision models, they are parallel architecture. They have several layers. For example, the modern computer vision models, convolutional neural network, vision transformer, generative adversarial networks, they all are having millions or billions of parameters, and they are computationally expensive to train the multiple layers. They have a convolution layer, they have an attention mechanism, and along with to train them on the large data sets, they require HPC systems. And this is just a short about how CNN model looks like and why what special they are, so that they can train in the HPC systems, and how they can be parallelized and in a efficient way. We know that the CNN models have various parallel tasks to implement. For example, convolution layers, they have several convolution layers, and they work in the matrix multiplication form. For example, the uh, data collected, for example, the processed images, then create the local receptors field. They all are processed in the matrix multiplication format, and these multiplication data are further very well suited for the HPC system environment, so that they can process in the parallel manner. CNN also have the batch processing. They are also well suited for the HPC system in parallel manner. Pooling layer, they also support in the parallelization. Multiple filters and channel, they also support the parallelization. So here we can see that the vision model, for example, the very basic computer vision model, which is the convolutional neural network, it has everything which can a researcher can implement them in the parallel manner on the HPC system. So I took this example CNN because this is a very basic computer vision model. Based upon this, we can build our understanding that what can be make parallel for the HPC systems, and how the advanced vision models, which are somehow based on the CNN, not exactly the CNN architecture, but based on the principle of parallel model of the CNN, they can be a process in the parallel manner. So here we see that all the components can be processed independently on the parallel HPC system. This was just an example. Here it matters the need of modern computer vision. Training such deep architectures on a single machine is very slow, and especially with the large data set, we cannot train them on simple machines. We have seen that there are various parallel opportunities for the basic computer vision models to train them in a parallel manner, and HPC environment, HPC cluster, let's say, allow them to train in a parallel manner. For example, they can be trained on the multi devices, 4 TPUs, 8 TPUs, 16 GPUs, multi GPU, and multi node scenarios. So we are all set to talk about how these computer vision models are ready for the HPC system. In fact, they are training on the HPC systems. We will see how these large vision models, which have the uh, latest technology, latest architecture of these models, for example, transformer, how they can be parallel for the training. So first, we will understand what exactly the large vision model is. Here, the large vision model is the deep learning computer vision model. Especially, these are designed for the understanding of the large visual data. Visual data are images and videos, where videos are the spatial temporal data. They have a temporal dependency of the images in the time frame at a very large scale. So, and yes, the main objective of the large vision model is making it more generalization. It means, unlike the traditional computer vision model, which heavily rely that one model will perform the one task. For example, one model which is trained only for the image classification task, they will perform only image classification tasks. Another which is trained on the object detection, they will only do that one. But here in large vision model, the researchers are trying to develop a single model which can handle all the tasks for the below task. You can see here, this can be performed with the single model. It means we are, with the research of large vision model, we are making it more generalization. So here are some characteristics of a large vision model, which is aiming to understand why, how it is going towards the generalization, which is the ultimate goal of the large vision model. They are very huge in model size. They have a very large data sets. Currently, I am working with the 5 data sets. So, so it is not like a single data set for single model. It is like multiple model as getting trained with the multiple data sets, because the goal is to make it more generalized. And advanced architecture, the large vision transformers, video vision transformers, and so many multimodals are developing for the large vision models, because they can handle these multiple tasks. Here the question is, whether large language model inspires the large vision model, or they are leading their own journey. So as a AI HPC researcher, I can say yes. The answer is yes. LVMs can be viewed as a counterpart of the large language model, because they are inspired in many ways, not only the way it is getting trained, but in the way they are scaling, they are owning the complex architectures. Here we can see how LLM is inspiring the LVM. First of all, the scaling, we have seen that GPT model, they are trained very well for any unseen data. It is just because they are getting trained day by day. It means making it scalable with the more data, with the more data and more complex architectures. In the same way, large vision model has been proven good generalizability with the scaling of the existing computer vision models, which are trained on the large data set, and by adding some layers on the existing architectures in the transformer model, vision transformer models. Yes, LLM also inspires to LVM in terms of the transformer architecture. They are the basic block of the large vision model. Like transformers have proven very good for the large language model, but in GPT, similar way, vision transformer and video vision transformer, they are showing a very good ability for the visual understanding and capturing the long-term dependency of the data. It is also inspiring in terms of generalization and zero shot learning. What does it make? Zero shot learning is, even if that model is not trained on that data, but still it should have ability to predict in the newer environment on the unseen data. So large language model has shown this kind of generalizability. LVM is also on the same way, making it more generalizable on the as a zero shot learning. It means it should predict the object, the scene, the action recognition, for example, in video data, even on the unseen data. So these kind of research are ongoing, which are really inspired by the LLM. Now I'll talk in short about the current state of the art large vision models. I'll not take too much time over here, because our objective is to understand how these models, LVM models, are getting parallel training on the advanced accelerators. So some LVM models are Florence 2. You can see here they are trained on 500 billion text annotations, 1.3 billion text region annotations, 3.6 billion text phrase annotations. So you can understand how big this model is, and they can handle the captioning, object detection, grounding, segmentation, and so many tasks with the single model, because they are trained on this big data set, right? Florence 2 is developed by the Microsoft. This is the framework here. Just a question: if we give what is happening in this scene, what are the different objects in this scene, who is there, what is happening. This is the input, and the right side you can see they are the output in the more generalization capability. It means the model should explain what is happening, who is there, how many objects are there, and segmentation of those objects. These all are happening with the single model. Here, this is the database. Dataset of Florence 2 is the FLD5P dataset. Another is the CLIP by OpenAI. It is the contrastive language image pre-training. This is also a very big model with the zero-shot learning. Another is the Polygamma by Google DeepMind. They are also having the language and vision capability. They are large language vision models, not only the large vision models. They have a capability for the general task as well. I gave this idea of the current state of the art LLM models because the researchers who audience who have joined and those who know what is happening in the large language model research and what are the available models they can also train and they can use it. So this is just an example. We will see how vision transformer models ideal for the parallel training. They have the layer independence in transformers, self-attention mechanism, matrix multiplication, token-based processing, scalability in large models. So these features of large vision model is enough to demand for the parallel techniques on the HPC systems, right? Here, I'll talk about the different ways of parallelization, hardware accelerator types. Does it really support the parallelization and choosing the right accelerator for the LVM training? Several ways include the data parallelization, model parallelization, hybrid approach, pipeline parallelization, sharded training. So in data parallelization, all the model is copied as it is on the different devices, and data is partitioned in among the devices. And the goal is to speed up training execution by dividing the workload, means dividing the data where data is utilizing in the chunks by the models. This is how it looks when it parallelize on the GPU system. Multiple GPUs are having the model copies exactly same, but data is getting split. So when to use data parallelization in the large vision model? When model fits into a single device memory, data set is large, and to simple scalable approach. It means data model is not that much big, but data is big. Then in large vision model, definitely you should use the data parallelization approach. In model parallelization approach, for the different devices, model itself split into the different computing devices, and it has, for example, as we have already discussed as a background, that CNN or transformers has the multiple layers and it matrix multiplications. So these layers can be divided into the component format and computed independently. This is how it looks like the model parallelization. Here different layer 1, layer 2 are running on the portion 1, portion 0, and layer 3 and 4 are running on the portion 1, and these two are running on the GPU 0, GPU 1, 2, and 3. That is how we distribute the model and the several layers. Framework for the data parallelization are TensorFlow and PyTorch for distributed training, or about for multi-GPU if the training is happening on the GPU system. In PyTorch, torch.nn.data parallel, that kind of functions we can use for the GPU. And for multi-node, we need MPI or NCCL, which is provided by the NVIDIA. We need to have in our system if we are training them on the GPU system. And model parallelization when model is too large to fit into a single device, when workload is compute bound, and splitting the model across devices allow better utilization. So the model parallelization can be done using the manual approach, using the GPUs by assigning IDs in TensorFlow and PyTorch framework, also with the Megatron LLM developed by the NVIDIA. This is how it looks like when data parallelization and model parallelization works. There are also a hybrid approach in which we combine both the way, and this is very effective for the large vision model, because in large vision model we have seen there as a very deep architecture of the transformer, and we have two very huge data with multiple data sets, so we need to have the both data parallelization and model parallelization approach. Okay, for hybrid parallelization, deep speed and fair scale for of the Facebook, they are very helpful for implementing them. This is how we can do the comparison before implementing the data parallelization model or hybrid parallelization approach of large vision system on any of the devices. Another is the pipeline parallelization, in which multiple tasks is divided, in which whole model is divided into the multiple tasks. This is also a good approach for the vision transformer. And GPipe, deep speed, and fair scale, they support the pipeline parallelization for the large vision model. Another is a sharded training, which is where optimizer state model weights, they are getting shared across the multiple devices. Another is the tensor model parallelization, where the tensor of a GPU is divided into the multiple parts. And this approach is only for the GPU, where TensorFlow is supporting. And here, just a short look on how the specialized hardware accelerators are designed for to support the large vision model training. I'll talk only about the NVIDIA GPU, TPU, and Graph-core IPUs. NVIDIA GPU support the data parallelization, model hybrid, and tensor parallelization within the framework of Horowitz, DeepSeek, PyTorch, distributed data, and TensorFlow mirror strategy form. And TPU, which is the tensor processing unit by the Google, they are specially designed for the tensor operations, which are the fundamental of AI algorithms. For the matrix multiplication, heavily they are specialized for. They also allow the same type of parallelization, data model, hybrid, and tensor. This is how the TPU looks like, how in a matrix multiplication unit. For TPU, we use the TensorFlow TPU strategy, and for the PyTorch, they have an XLA approach where they can use as a plugin. I'll not go into the code. Okay, I'm very much interested to talk about the intelligent processing unit, which has been until now proven the best accelerator for the large vision model, along with the hybrid parallelization approach. They are especially designed for the vision task. They do not require any patch size for the parallelization. Instead, they rely on the compiled graph. They are well suited because of the several reasons. They have a massive parallelization, efficient memory, high computational density, and they have their own popular SDK, which supports all the several parallel training approach. Large visions for the TPU accelerators, they involve both data parallelization and model parallelization. They are data heavy, and compute intensive tasks they can handle. This is how the SDK of IPU looks like. They support type framework of TensorFlow and PyTorch, along with others SDK as well. They have a popular SDK, TensorFlow and PyTorch integration for the IPU optimized framework. They use data and model parallelization. The data parallelization with the popular graph. It is how it works. Also, the model parallelization. The model parallelization worked with the popular SDK for the better support in the IPU with the PyTorch and TensorFlow. This is how it works with the software stack of the popular. I'll not go into the detail of when you should use the GPU, TPU, or IPU, but I have concluded over here that TPUs for the large scale dense model, they are well suited. No, I'll start with when you are ready. When you are beginner at the LVM, you should choose the GPU because of their flexibility of the different framework. When you are at advanced at the LVM, you should go with the TPU for the largest scale dense model. But if you have a multi-model LVM and you have a very deep architecture of vision model, then definitely you should focus on the IPU on in the hybrid parallelization model. These are the takeaways. Large vision model are the future of AI with the potential of multimodal capabilities. Integration of LLM can definitely make them more generalized. They are greatly benefit train in the hybrid parallelism approach and choose accelerator wisely. GPU, TPUs, and IPUs are the powerful accelerators, but they have proven their own capabilities. For LVM inferencing, you may require different HAI accelerators since they are not for the inferencing, they are only for the training purpose. Okay, here I'm happy to answer your questions. Please, if you have any questions.
Thank you very much. Thank you very much for this presentation. It was extremely interesting. We've actually learned a lot about different ways to go when we want to do parallelization on HPC systems. Thank you very much for giving us the time to explain the different venues to do parallelization on HPC systems. I don't know if anyone from the audience has any questions. So we're gonna wait for the audience to type in their questions. Maybe I have a couple of questions.
Please.
The first one is actually, so first, I really like that you gave the state of the art, as you said, for people who are just starting, for them to know what is actually going on and what things are actually there so that they don't, implement things from scratch and to use what's actually there. And I mean, it's always a good idea to know what's in the literature before you jump into any field or any topic. So that was actually very interesting. So my question here is when you have, for example, like a model, and it's kind of in my head, it's kind of like a trade-off between the computational efficiency and the model accuracy. Do we have to I don't know, give up on one of them to achieve the other one, or can we actually do both with different, I don't know, with different levels?
Very nice question. Actually, this is the very common question to all the researchers when they start their work on the different accelerators. So for this, I would say if you are sure about you should achieve this much of accuracy, you should not stick with the single accelerator. You should definitely switch to the different one. For example, the vision model you train on the GPU system, they are not giving the good accuracy, along with they are taking the long time in the model parallelization approach. Definitely you should try the hybrid approach with the IPUs, which is taking the less time. I mean, you will definitely get the different result. Then you can compare and you can come up with the final outcome.
All right. Okay. That makes sense. Aya and Intisar, they're saying thank you so much for the interesting presentation. And Dr. Ahmed is actually asking, so I'm going to display the question for you so that you can also see it. What is the difference between IPUs and TPUs in the architecture point of view?
See, TPUs are especially for the tensor operations. They are the heavily depends upon the tensor architecture for the matrix multiplication. But IPUs are the wafer on wafer. They have a different layer-wise architecture. They are not only for the matrix multiplications. They are also for the other specializations. whereas TPU heavily depends only for the matrix multiplications. So this is just a short answer which I can give in this short time. But yes, they are different, and IPUs are specially designed for the all the vision processing tasks.
Okay, thank you very much. I hope this answered the question. I don't know if there are any other questions from the audience. It was actually also one thing that I really liked is that table that was somehow like a roadmap to know where to use what, right? This was
Exactly.
actually also, yeah, very interesting because, you know, it's like you took a lot of information and then put it in a structured way so that people don't get lost. So if I'm looking
Exactly.
into, yeah, if I have a specific problem, then I know exactly what to look for and then which way to go. That's
Yes, yes.
actually,
In this way, I would suggest first you look at the table of the accelerator, which accelerator
mm,
is needed for your kind of application. Then you check the parallelizing approach, in which parallelization techniques you should go. So once your accelerator is decided, and then you should go for the parallelization techniques. For example, for hybrid approach, model parallelization, whatever.
yeah.
So
Exactly. Yeah, this was actually very interesting for me because it's always like somehow very broad, so we don't know which way to go. So it's good to have some sort of like
yeah,
structured and organized, yeah,
Safa, I
information.
would also like to ask to you and audience if they want to connect and know more about how large vision model is working and how HPC accelerators are working for the different vision models. If they want to know more about and they want to connect with me on my ongoing research, they can connect with me on my given email ID, and they
Okay.
can do the QR code. They can send me the LinkedIn
Mhm.
invitations and all. I would be
Yeah.
happy to answer them over there because I know this is very short time in the,
Yeah.
in this short time. This is very big topic, and covering all
Yeah.
them is not possible.
Yeah, that's right. So here we have all the contact info from Dr. Sharma, so everyone can feel free to like reach out. We have two more questions. We have a question from Cesar. So again, I'm going to show it here. She has a question about pipeline parallelization. How we can optimize the computation of mechanisms for transformers when capturing long-range dependencies in LLMs and global information in LLMs.
All right. So I would focus more about the last part of this question, which is the global information in the large vision model. In the pipeline parallelization approach, you completely break your architecture, or for say the working model of the architecture in a different pipelines, different is small works. Where one portion of that architecture is complete, the output of that is sent to the another one, but they are heavily working on the independently. So the computation mechanism for the transformer, if you are asking about the capturing long term dependency, but yes, you should carefully divide your model into the different pipelines so that dependency of one pipeline, one chunk of the model can be easily transferred or understandable as an output to the another parallel to the another chunk of that architecture. This is how it works, and long range dependency can be captured in the large vision models.
Mhm. All right, thank you. I hope this answered your question, Cesar. And then Dr. Imad is also asking, are there any platforms offering IPUs?
Actually, I was waiting for this question because when I was trying to get IPUs on the different HPC clusters and all, I got stuck from where to get it. You can ask if you are connected with your university. Definitely, you can get from access from there. Otherwise, GraphCore, who designed the IPU, they also
Mm,
have some cloud mechanism. They have several pricing models and all. You can check over there. I got the IPU from my university's access HPC system.
okay, perfect. All right, thank you very much. Thank you very much, Dr. Sharma, for this presentation and for answering all the questions. It was really, really interesting to listen to your presentation and also to listen to your answers. Thank you very much also for offering, for like giving your contact information for our audience to reach out to you later. That's actually very nice of you. Yeah, it was really a pleasure having you, and we're looking forward to more collaborations in the future.
Sure. I would be happy to collaborate with any of the HPC AI researchers
Thank
and
you.
go ahead with the large vision model research.
Mhm.
Thank you, Safa. Thank you, audience who joined you to listen me.
Yeah, thank you very much. Thank you
Thank
very
you.
much for our attendees. Yeah,
Thank you. Bye.
thank you. Goodbye, all.
Bye.